Motion is one of the first ideas we think we understand. Something moves because it changes position. A car travels down a road. A planet circles a star. A person walks across a room. Motion feels like pure common sense. So basic that it hardly seems worth questioning. Objects exist in space. Time ticks forward. And motion is just what happens when something shifts from one place to another as time passes. Hidden inside this simple picture is an assumption, so deep we rarely notice it. We assume that motion happens within reality, not that it alters reality itself. Whether a train is parked or speeding down the tracks, we imagine the world underneath remains the same. Space is still space, time is still time. Motion feels like a change of scenery, not a change of structure. This assumption works beautifully in daily life. If you toss a ball on a moving bus, it behaves exactly as you expect. You catch it without thinking about your speed relative to the road outside. Your brain quietly subtracts motion and preserves a stable picture of the world. This success reinforces the belief that motion is relative but harmless. Different observers may disagree about speed, but they all agree about what exists. For centuries, physics shared this comfort. Even after Galileo showed that motion is relative, the underlying stage remained fixed. Space was absolute, time flowed evenly for everyone. Objects moved through the stage, but the stage itself did not respond. Motion changed trajectories, not reality. This is where the trap lies. The idea that motion is merely positional change assumes there is a deeper layer that stays untouched. It assumes there is a universal background against which motion can be measured without consequence. We rarely question this because nothing in everyday experience seems to contradict it. Feynman liked to warn that the most dangerous mistakes in physics come from ideas that feel obvious. Motion is one of them. When examined carefully, motion refuses to stay confined to position alone. Once measurements become precise enough, motion begins to leak into things we thought were untouchable, like time itself. At first, this sounds absurd. How could moving faster possibly affect how long a second lasts? A second feels like a second no matter how you move. Yet this confidence comes from living at speeds where the effect is too small to notice. Physics is not obligated to preserve intuition outside the narrow conditions where intuition evolved. The first crack appears when we ask a deceptively simple question. How do we compare events that happen at different places? To do that, we must agree on clocks. We must agree on what at the same time means. And here, motion quietly re-enters the picture in a way no one expects if two observers are moving relative to each other. Which one measures time as it really is? Classical thinking insists there must be a right answer. Even if it is hidden, relativity refuses this comfort. It says there is no single correct clock ticking beneath appearances. This is the moment when motion stops being a passive detail. It starts interfering with the definition of time itself, not metaphorically. Literally, different states of motion lead to different measurements of duration, and no experiment can reveal which one is wrong. At this point, many people instinctively retreat. They assume this must be an illusion caused by signal delays or measurement tricks. Surely, once corrections are made, reality will snap back into alignment. But the corrections have already been made. The disagreement survives. What makes this unsettling is not just that motion affects measurements, but that it does so consistently and lawfully. There is no chaos here. There is structure. Motion reshapes how space-time is divided, and all observers follow the same rules while disagreeing about the outcome. Feynman loved examples where the universe forces you to abandon comforting pictures. Motion is one of those cases. What looks like a simple change of position turns out to be a change in how reality itself is organized. The world does not sit still while objects move through it. The world responds. This realization does not arrive with drama. There is no single experiment that screams its conclusion. Instead, motion slowly reveals its deeper role, eroding the idea of an absolute backdrop. By the time you notice what has happened, the old picture is already gone. Motion no longer feels like a surface detail. It becomes a probe, a way of uncovering the hidden geometry of reality. And once that geometry is exposed, it becomes impossible to maintain the belief that motion merely rearranges things without changing what they are. The real trouble begins when physics asks for precision. As long as motion stays slow and distances stay small, everyone can pretend that differences are minor and easily corrected. But once measurements become exact, a surprising fact emerges. Observers in motion do not merely report different numbers. They disagree about the structure of events themselves. Imagine two observers passing one another, each carrying clocks and rulers. Common sense insists that if they are careful enough, they should be able to translate their measurements and recover a single underlying reality. One might be moving, one might be still, but surely one description must be more correct. This expectation feels unavoidable. Reality, after all, should not depend on who is looking. Einstein's insight was to challenge a different assumption instead. He insisted that the speed of light must be the same for all observers, no matter how they move. This was not philosophical stubbornness. It was forced by experiment. Light did not behave the way absolute time required it to behave. When physicists accepted this fact and followed its consequences honestly, agreement collapsed. If the speed of light is the same for everyone, then time cannot be. Clocks in motion must tick differently. Distances along the direction of motion must change. Most unsettling of all, simultaneity must become relative. Two events that one observer calls simultaneous will not be simultaneous for another moving observer, even after correcting for signal delays. This is not a trick of perspective. There is no hidden master clock running behind the scenes. Each observer's measurements are internally consistent and equally valid. Physics offers no method to declare one viewpoint privileged. Motion strips away the idea of a universal now and replaces it with many equally legitimate slices of reality. At first, this sounds like mere disagreement about labeling, but the disagreement has teeth. If two observers cannot agree on what is happening now, then they cannot agree on what belongs to the past or the future. Events rearrange themselves depending on motion. An occurrence that lies in one observer's future may lie in another's past. This is where intuition finally breaks. We are used to thinking of time as a single ordering shared by everyone. Relativity denies this. It says that ordering is not absolute. It is woven together with motion and space into a single structure called space-time. Feynman emphasized that this result is not negotiable. It does not come from clever philosophy, but from insisting that experiments mean what they say. If light behaves as observed, then space and time must behave differently than we imagine. There is no smaller adjustment that saves the old picture. Once observers stop agreeing, the idea of motion as a harmless change dissolves. Motion becomes a way of carving reality differently. Each observer carries their own grid of space and time, and these grids tilt relative to one another. None is wrong. None is fundamental. This realization forces a quiet shift. Reality is no longer something that sits fully assembled behind appearances. It is something that depends on relations between observers. What exists does not change, but how existence is divided into before, after, and now does. The shock is not that physics allows disagreement. The shock is that it demands it. The laws themselves insist that no observer gets the final word. Motion removes the possibility of a single authoritative timeline. This is the point where motion stops being about speed and starts being about perspective. Not psychological perspective, but physical perspective, encoded in space-time itself. The universe does not ask who is moving and who is still. It only asks how they relate. Once this is accepted, the door opens to a deeper realization. If motion changes how time and space are organized, then motion is not distorting reality. It is revealing something that was always there, and that realization carries consequences far stranger than disagreement alone. Once observers stop agreeing, the instinctive reaction is to assume something has gone wrong. Surely motion must be distorting measurements. Surely clocks slow and rulers shrink only because of observational tricks. This response feels natural because it protects a deeper belief that there exists a true version of reality hiding underneath all this disagreement. Relativity refuses to grant that comfort. It says there is no hidden, undistorted layer waiting to be uncovered. The effects of motion are not illusions. They are the correct description of how space-time itself is structured. Time dilation is a perfect example. When a moving clock runs slower than a stationary one, nothing is malfunctioning. The clock is doing exactly what the laws of physics demand. Every physical process inside that clock slows down in the same way. The ticking mechanism, the atoms, the chemical reactions, all evolve consistently. From the clock's own perspective, nothing unusual happens at all. The same is true for length contraction. Objects moving at high speed are not being squashed by motion. Their spatial dimensions are being measured along different slices of space-time. Motion changes how space and time are mixed together, and what appears as contraction is simply the geometry revealing itself. Feynman was particularly clear on this point. He rejected the idea that relativity effects are observational artifacts. He emphasized that they are as real as anything else physics describes. When two observers disagree about lengths or durations, they are not seeing different versions of the same reality. They are each accessing reality along different directions in space-time. This is the key shift. Motion does not bend reality out of shape. It exposes the shape reality already has. To understand this, imagine space-time as a four-dimensional structure rather than a three-dimensional world evolving in time. Each observer, depending on their motion, slices this structure differently into space and time. These slices are not subjective choices. They are determined by the observer's state of motion. Change the motion and the slice tilts. What looks like time dilation from one perspective looks like length contraction from another, but both are manifestations of the same underlying geometry. Motion is not adding strange effects on top of reality. It is selecting a different cross-section through it. This is deeply counterintuitive because human intuition was built to survive, not to understand space-time. At everyday speeds, all reasonable slices look nearly identical. Differences are too small to matter. Evolution never forced us to confront regimes where motion significantly alters the geometry we experience. Physics, however, is not constrained by comfort. It follows consistency. And consistency demands that if light speed is invariant, then space-time must be flexible. Time and space must trade roles, depending on motion. Once that trade is accepted, the effects stop looking mysterious. They become necessary. One of Feynman's strengths was his refusal to mystify this conclusion. He treated it as a fact to be absorbed, not a paradox to be feared. The universe, he argued, is under no obligation to match our mental pictures. Our pictures must adapt to the universe. Seen this way, motion becomes a diagnostic tool. By changing how an observer moves, physics probes different aspects of space-time structure. High-speed motion reveals relationships that remain hidden at low speeds. The faster you move, the more of space-time's geometry becomes visible. This reframing dissolves the idea that there is a single true measurement of time or space. There is only the invariant space-time interval, a quantity all observers agree on even while disagreeing about how it splits into space and time. Agreement moves to a deeper level. What feels unsettling is realizing that the reality you experience is not the whole structure. It is a projection, a valid one, but not a complete one. Motion changes the projection, not the underlying space-time. Once this is understood, the phrase motion warps reality takes on a different meaning. Motion does not warp reality like a lens bending light. It reveals that reality was never flat to begin with. The warping is not introduced by speed. Speed merely uncovers it. This is why attempts to restore absolute time always fail. They are attempts to deny geometry. Relativity does not say motion creates strange effects. It says motion uncovers the rules by which space and time are stitched together. At this point, motion can no longer be dismissed as secondary. It is not a detail layered on top of reality. It is a key to understanding its structure. And once motion is seen this way, a deeper question inevitably follows. If motion reveals space-time's geometry, what happens as motion approaches its ultimate limit? As motion increases, the effects that once seemed negligible begin to dominate. At low speeds, time dilation and length contraction are so small they can be ignored. At higher speeds, they become impossible to escape. This is not because something new suddenly happens, but because the underlying structure that was always there becomes harder to overlook. One of the most persistent intuitions is that speed should add up. If you walk inside a moving train, you expect your speed relative to the ground to be the train's speed plus your walking speed. This works well until light enters the picture. Light refuses to cooperate. No matter how fast you chase it, it always pulls away at the same speed. Physics does not treat this as a curiosity. It treats it as a rule. To preserve this rule, space-time pays a price. As speed increases, time stretches. Processes slow down. Clocks tick more slowly, not because they are damaged, but because time itself is being divided differently. The faster you move through space, the less you move through time. This trade-off is non-optional. It is built into the geometry. Acceleration then becomes the real challenge. Each push toward higher speed demands more energy than the last. As velocity approaches the speed of light, the required energy grows without bound. This is not an engineering limitation or a failure of technology. It is a statement about space-time itself. The structure of reality resists being pushed beyond a certain boundary. Feynman emphasized that nothing mysterious is blocking the way. There is no cosmic speed police. Instead, the rules of space-time simply do not permit massive objects to reach light speed. The closer you get, the more extreme the distortions become. Time slows dramatically. Lengths compress. From the outside, a fast-moving object appears almost frozen. From the object's own perspective, something stranger happens. It never experiences reaching the speed of light. Proper time continues normally. The limit exists not as a felt barrier, but as a boundary in the relationships between observers. The closer an observer comes to light speed relative to you, the more their timeline stretches relative to yours. This reveals an important fact. The speed of light is not just a speed. It is a conversion factor between space and time. It sets how much space can be traded for how much time. Trying to exceed it is like trying to rotate beyond a right angle. The geometry does not allow it. What makes this unsettling is that motion does not merely affect moving objects. It reshapes how the universe can be explored. High-speed travel alters aging, synchronization, and causality boundaries. Different observers carve space-time into different regions of what can influence what motion redraws the map of cause and effect. Yet none of this is chaotic. All observers still agree on deeper invariance. The space-time interval remains the same. Laws remain consistent. What changes is how those laws appear when projected into space and time separately. This is the true cost of moving faster, not danger or destruction, but estrangement from familiar intuition. The universe does not reward speed with freedom. It demands payment in altered time and distorted space. As motion approaches its limit, reality becomes less like a stage and more like a structure with strict rules. Speed does not break those rules. It reveals how rigid they always were. By the time this is understood, motion no longer feels like an attribute objects possess. It feels like a relationship that reshapes experience itself, and that realization prepares the ground for the final step, understanding what motion ultimately teaches us about reality, beyond speed, beyond observers, and beyond intuition itself. After motion has stripped away the last comforts of intuition, one lesson remains. Motion does not complicate reality. It simplifies it by exposing what is fundamental. Space and time are not separate arenas stitched together by motion. They are inseparable aspects of a single structure, and motion merely reveals how they trade places depending on perspective. This is why relativity feels less like a theory about speed and more like a theory about humility. It tells us that the universe is not built around human experience. The rhythms of clocks and the lengths of rulers that feel natural to us are not universal standards. They are local habits formed under specific conditions. Feynman often stressed that understanding comes from accepting what nature does, not from insisting on what feels reasonable. Motion teaches this lesson mercilessly. It forces us to abandon the idea of a privileged viewpoint. No observer, no matter how slow or stable, gets access to reality as it truly is. Each observer gets a consistent partial projection. What physics preserves instead is invariance. While observers disagree about time and distance, they agree on deeper quantities. Space-time intervals, causal structure, and physical laws remain intact. Agreement moves beneath the surface. Reality is not what is measured individually, but what survives every possible measurement. This shift has practical consequences. Technologies that rely on precise timing, such as satellite navigation and particle accelerators, work only because relativity is taken seriously. Motion's effects are not philosophical curiosities. They are engineered into systems that function every day. The universe quietly enforces its rules whether we acknowledge them or not. The deeper implication is more unsettling. If motion reshapes time and space, then the world is not a sequence of snapshots evolving in time. It is a network of events connected by space-time relationships. Motion changes how those connections are experienced, not how they exist. Seen this way, motion becomes a teacher rather than a troublemaker. It reveals that reality is relational properties like duration and distance are not absolute possessions of objects. They arise from how objects move relative to one another. This does not mean reality is subjective. The rules are strict. They apply equally to all observers. But they are not anchored to any single perspective. Truth in physics lies in relationships, not in isolated measurements. The discomfort many people feel toward relativity comes from expecting the universe to honor common sense. Motion shows that common sense is a local approximation, not a guide to fundamentals. At low speeds, it works beautifully. Beyond that, it misleads. Feynman believed that this confrontation with counterintuitive truth is not a flaw but a gift. It forces clarity. It forces us to separate what feels real from what is real. Motion is one of the sharpest tools physics has for making that separation. In the end, motion does not warp reality into something strange. It reveals that reality was always stranger than we assumed. The world is not built from stillness disrupted by movement. It is built from relationships that only appear simple when motion is slow and differences are small. Understanding this does not make the universe more comfortable. It makes it more honest. Motion shows us a universe that is consistent, elegant, and indifferent to intuition. Accepting that indifference is the price of understanding. And once paid, motion stops being a puzzle and becomes a guide, pointing toward a reality deeper than appearances, where speed is not just motion, but a window into the structure of existence itself.